Passive house. What is a passive house? A building comprises set design principles used to attain a quantifiable and rigorous level of energy efficiency with this specific quantifiable comfort level. Optimize your gains and losses based on the climate summarizes the approach. To that end, a passive building is designed in accordance with these five building science principles, according to the article. They are to conserve energy, have less emissions emitted out from the building, less emissions throughout the building because the building is airtight, which has little to no cracks in it at all. Another principle is that it allows for use of solar energy, the use of solar panels and the sun's radiation. The high performance allows also a source of light throughout the house. Instead of having actually to burn electricity, you can just use the natural light from the sun. As pictured above, the house to the right, you can clearly see they have plenty of windows, and the house to the left is covered in solar panels. Another principle is that it contains a perfect balance of heat and moisture, allowing the house ventilation to run smoothly throughout the house. Lastly, there's minimal space conditioning is also the last principle of a passive house. Passive house continued. Other elements that create a passive house is the triple glazed windows and doors, allowing them to catch more sunlight and radiation, allowing natural light to accumulate in the house instead of using electricity. Solar panels allow for almost net zero building. The passive houses are on the right path, becoming a net zero and net positive, meaning they do not give off or take in any carbon. Typically, these houses are more expensive than your average house, coming in around 5 to 10% more. While passive houses are airtight, they also are super isolated, allowing little moisture to seep through, causing little to no mold in the house. Not one passive house is the same. They're all built differently. How is North America's approach to balance ventilation implemented? The main factors when it comes to North America in approaching balanced ventilation is usually follows these four core principles: biology, architecture, technology, and climatology, as pictured to the left, which all work together in trying to balance ventilation throughout North America. Those are considered the interlocking fields of climate balance and ventilation. The PHIUS is short for the Passive House Institute of the United States, has many different builds when it comes to the different climates throughout. Places like Florida, where it's more moist and more wet, the buildings are different than the ones you find up north where the climate is much colder and drier. According to this article done by Smith, three main issues is in low load airtight homes were addressed. Number one, ventilation losses were reduced through a centrally placed whole house ventilation system with heat recovery. Two, indoor pollutants such as moisture, CO2, radon, and VOCs could not be controlled for occupant health. And three, hydrogeothermal performance of the envelope resulting in superior durability was greatly enhanced. The envelope is what they call the airtight insulated around the whole house. There are plenty of studies going about how to balance ventilation throughout the US, and the studies are happening in zones where the climate is different and there's constant weather changes. The focus is designing climate-specific, airtight, highly insulated buildings, enclosures with integrated micro-load mechanical systems. First to meet stringent climate specific energy standards, then add renewable energy sources to get close to zero, reach zero, overproduce, and eventually zero out carbon. Balanced ventilation systems remain an essential part of the design and the climate approach in the cold, mixing the hot alike. With or without heat recovery, a balanced ventilation system assists convection, and the redistribution of heat gains and space conditioning loads. There are many studies and recommendations with experts of how passive houses should be built, where they should be located, and the type of ventilation needed in that house to be balanced. Continued. Balanced ventilation remains an essential part of the design and specific approach in the cold mix alike. There are many studies done, as you can see to the diagram to the left. There, as seen in the building above to the left, the hypogeum cellar, which regulates the whole temperature of the house, is giving off little to no emissions. In North America, the balanced ventilation is implemented by climate outside. The sensors tell you the heater or the air conditioner to turn on and off based off the temperature of the building. Since this is a greener approach, many of the new buildings are built in the passive way and have more balanced ventilation. The image on the left shows, the image on the right shows what a perfectly balanced ventilation system in a house would look like and how much input and output are given. North America is starting to become more and more sustainable, so the newer houses will have this as an offer. It is slightly more expensive to have it originally, but it will offset your bills in the long run.
Insulation refers to the property of a house to absorb little heat during warmer months while retaining that heat during colder months. Super insulation goes beyond regular insulation, as the strategic trapping and releasing of heat is the primary method of heating the house itself. The basic properties of super insulation include the usage of thick insulation used on most of the house, the usage of a vapor barrier to prevent moisture from intruding on the system, an airtight construction of the house itself, and a focus on the exact climate and conditions of the site. As Shercliffe points out in his 1988 book, Super Insulated Houses and Air-to-Air Heat Exchangers, there is no single best set of values for insulation thickness, due to the climate of the house's location being the main source of the heat and the varying of climates around the world. Super insulation comes with a myriad of benefits, such as decreased utility costs, especially on heating, comfortability within the house itself, and the ability to be used in a lot of environments. The only main downside to super insulation comes with the upfront cost to install it. However, it is quickly paid for as you save money on heating and cooling. The simple illustration on the left showcases the difference between a super insulated wall and a conventionally insulated wall. As you can see, the super insulation thins the insulation while providing much more effective insulation and the inclusion of a vapor barrier. The diagram to the right showcases one instance of a super insulation system, which includes an air-to-air heat exchanger as well. The air-to-air heat exchanger takes the fresh air from outside, and transports it to the inside, and takes the stale inside air and transports it outside, tackling the interior humidity. A ventilation heat recovery system, sometimes known as air-to-air heat exchangers, heat recovery ventilators, or energy recovery ventilators, is a system in which heated air is dispersed into the structure while cold air is ejected out of it. Not only does this warm interiors, it additionally expels stale air outside, allowing for a more comfortable interior. This warmed air, which is kept inside, is additionally retaining the energy of the house's interior. Some benefits to ventilation heat recovery include more comfortable interiors, energy-saving properties, lowering of heating and cooling costs, prevention of damage to the structure, such as mold, and an improvement to occupants' health. Speaking to the last point, these systems can remove harmful pollutants from interior structures, such as radon, formaldehyde, excess moisture, smoke, and carbon monoxide. As such, these systems not only heat a structure, but also assist in the prevention of sick building syndrome. Referring once again to the image on the left, a clear example of a ventilation heat recovery system is shown alongside super insulation. These two systems work together in order to ensure that the warm air brought inside by the ventilation is not lost through this super insulation. The image on the right showcases the ventilation heat recovery system itself. In this example, the fresh, cold air enters the machine through the top right and exits as fresh, warm air on the bottom left. Once the air becomes stale, it is pumped out through the top left and used to warm the incoming cool air, only to be ejected after cooling down the bottom right. Airtight envelopes refer to a building having no points for air to unintentionally enter or exit a structure from. This house property is often known as airtightness, building airtightness, and/or envelope and airtightness. Airtightness is such an important topic, as with spaces that air can escape from comes energy loss in houses. Energy loss not only can rapidly disrupt the internal temperature of a building, but it can also lead to a drastic increase in heating and cooling costs. Additionally, the losing of warm air during winter can increase the condensation buildup on the frame of the house, potentially leading to rot or mold buildups. Some of the benefits of airtightness include a lowered heating bill, reduced structural damage, improved ventilation of the structure, and a greatly increased control over the thermal comfort of the structure. The illustration on the left serves as a simple demonstration of the reasons why air would enter or exit a structure. As the left side shows, climate can cause an influx of cooler air, while the heat difference outside, demonstrated here on the right, can suck air out of the house through non-airtight locations. The image on the right is a helpful demonstration of areas that air could leak from or to if not properly sealed. However, with a designer focused on making an airtight envelope, these leakage sites can be patched and strengthened. Thermal bridges refer to areas of the thermal envelope of the building in which weaknesses allow for heat to slip out. Typically, thermal bridges appear at the joining of two separate elements of a house, such as between a wall and the floor or a wall and another wall. Thermal bridges are a huge problem when trying to design a passive house, as they allow the retained heat to escape outside and create cold spots within the house, which can lead to the growth of rot or mold in the walls. Through employing airtight methods such as a vapor barrier, insulation, or properly sealing the junctions of a house, thermal bridges can be avoided. The diagram on the left illustrates an overly simplified indicator of where thermal bridges can emerge due to the joining of two elements. As this is a simplified model, thermal bridges are not guaranteed to form at such positions. However, they are likely to if proper sealing has not been done. The heat indicating diagram to the right showcases three examples of heat within a joint of the structure. The leftmost image indicates a thermal bridge in which warm air from the structure is being sent outside while the cold air replaces it. The second image showcases a typically insulated corner in which there's still some heat loss, allowing for a tiny thermal bridge to form. In the final image, however, the efficient corner illustration, there is no instance of a thermal bridge in which heat is being trapped outside, as the heat is being trapped inside and the cold air is being left outside. And cut.
So in this slide, I'll be talking about early passive design for homes in the United States. So on the left, you see Nixon signing the approval of the APA. And in 1970, the White House Council and the US Congress worked with critical concern with the environmental state of the United States, in which they formed the EPA, also known as the Environmental Protection Agency. By doing so, they were able to formulate and mandate environmental performance-based codes and requirements on particular regions across the country that significantly improved the quality of construction being produced. This led in 1976 to the first performance-based approach rather than an individualized checklist to improve the basic qualities of a home. On the right, you see the Levittown, Long Island in the late 1940s, and this is after the GI Bill, after following World War II, and the quick expansion of home development without concern of the use of passive design. William Shercliffe in 1988 developed material elements and minimized mechanical systems to develop the principles of conservatism for the United States that forever shaped passive design. In what we consider first generation design of passive homes, we see a 60 to 80% loss of heat reduction, which is significantly less than the previous designs, therefore lowering the amount of point source heat sufficiency and contributing to better airtight construction. A negative attribute to this early form of design was that there was no mean of measurement to account for the total energy produced, and the only ways in which researchers were able to approach a quality assurance test was through an airtight test and solely based on the qualities of craft and craftsmanship principles. Not one solution works for every climate zone. Depending on the region, designers in passive systems must look at humidity levels, heating and cooling fluctuations of the environment, the materials due to erosion that they may use. An airtight envelope falls under the category of passive design, known as the envelope performance, focused around microloads, which stands for a building's ability to use minimal energy usage and consistently stay at that particular temperature over a long period of time, including power outages. By the 1980s, roughly 30,000 of these homes included these standardized technologies. And what we consider the first generation of design of the passive homes, we see a 60 to 80% loss of heat reduction, which significantly is less than the previous designs, therefore lowering the amount of point source heat sufficiency and contributing to better airtight construction. A negative attribute of this early design was that there was no means or measurement to account for the total energy produced. And the only way in which this research was able to approach a quality assurance was through an airtight test and based on the craft principles. As you can see here in this slide, in the 1970s and 1980s, US and the Canadian government allocated a significant amount of funded research in regards to passive design. This was due to the industry experiencing the effects of the oil embargo and how much it was costing the average citizen to heat and cool their own home during with these construction techniques. Zero Energy Ready Home, a US Department the U.S. Department of Energy so with the accommodation of the Zero Energy Ready Home U.S. Department of Energy, they brought back an acknowledgement of performance of base standards. In what we now consider the first generation of passive design homes, we see a 60 to 80% loss of heat reduction and was significantly less in the previous design, therefore lowering the amount of point source heat sufficiency in a better airtight construction, as mentioned on the last slide. And not one solution for every climate zone works. In particular, as you can see on the left, we see a climate map defining each of the zones of the United States themselves. And with each of that, we have a different take on how each of these areas reacts to different materials and how they better affect passive design. In the 1990s, European passive design, specifically in the German Passive House Institute, or the PHI, trying to instill thoughts and ideas into the German government. The first convincing breakthrough in which they had stemmed from Krankenstein in Dortmund, Germany. During the early 1990s, this home reached a factor of 10 reduction on the European climate zone. This was later introduced through the mass production of home through its low-cost energy design. As shown in the chart, ceilings, height, wall thickness, and floor or floor square footage took major considerable qualities towards it, so it could be considered a sustainable in its design approach. So as you can see, the performance-based test, considering square foot annually energy emittance, research to determine the quality of assurance through ventilation techniques, craft, and air tightness tests of the time. When we look at this particular project, its usage of materials, design implementation, such as the super insulation, high quality windows, ventilation, heat recovery, air tightness, and the avoidance of thermal bridges. By using these techniques, the project was able to use less than 10% of the energy of the building up to German building code during that particular time. This system of cooling for the home was quite complicated in the ways in which it allowed a system to pull exterior air and through the usage of solar energy, transform it into making a comfortable living condition of the occupants inside. Another element of it was its heating and cooling hold tank. Within that, it makes up approximately 50% of the energy consumption found within the ventilation system of the home itself. The heating coil and the holding tank are allowed through solar energy consumption and allow the energy to be contained and reused for other purposes throughout the home. Next, we'll look southward, facing window apertures. So by doing this, this creates a harsh, intense light that is found nowhere else in the home. And actually, it is one of the strongest forms of light. North is your consistent direction of light that you'll have consistent sunlight amounts coming in through that particular direction at all times of the day. But if you go from the southward direction, you actually get a very harsh light in certain periods of the day. And by doing so, it creates a temperate temperate view of the actual sun admittance into the home, therefore heating the space. So the window oriented south allows 44% of the house's actual heat requirement, not to mention the usage of entirely 100% solar paced or space heated system, allowing the building to not require external amounts of energy usage through an almost 100% hot water heating system as well. During 1975, when the house was completed, we see that it uses 5.1 gigajoules per year, and prior to this, a typical home in this area consumed approximately 140 gigajoules per year. The cost of construction of this home ranged to $50,000 during the time. In modern day, with inflation, this would have been a multi-million-dollar construction, and would have been now in today's world much more attainable through the development of technology and where we have come through in our breakthroughs in solar and passive design, and becoming more large scale and overall more accepting of the idea itself. And in this last slide, things to take into consideration is the heat and energy gain that could be found in the form of exterior components, but also internal components such as human occupancy, appliances, lighting, and a combination of exterior and air temperatures.